So going over the homework, the chain rule, applying the chain rule is basically doing a derivative twice, right? So the chain rule, just to recall, chain rule says that if you have a f of g of x and you want to do the derivative of that, it's the derivative of the outside, and you leave the inside alone, times the derivative of the inside. So you do the derivative of the outside times derivative of the inside. So let's look at 21. And again, you may have to apply other rules to this situation. Y is 1 over square root 3x plus 5. Square root 3x plus 5. All right, so there's a number of different ways we can approach problems like this, right? There's a number of different ways we can approach this problem. What is one way that comes to mind, looking at this question, number 21, what is one rule that comes to mind when you see this problem of how to approach it? What's one of a way you could do this? What rule comes to mind? You see this situation here. I mean, obviously the chain rule. We have this square root inside a problem, right? The square root on the outside, this thing on the inside. But what other rule might you apply in this situation? Anyone have any ideas? You look at this problem, you think, what rule of derivatives could I apply to this situation? Quotient rule, Perry. So yes, absolutely. One of the ways you could do this is using the quotient rule. We got a fraction, low d high minus high d low over low squared. That is absolutely legitimate. So one way we could do this is with the quotient rule. Totally fine and normal. And we'll do that. Another way that may be less obvious, because it's the top is not a the top part is not a function, it's just a 1. I could do this by looking at the problem like, remember this square root is the same thing as saying 1 over 3x plus 5 to the 1/2 power. Right? Square roots are also fraction exponents. You need to be able to see that that is equivalent. And since I have something with an exponent on the denominator, I could hypothetically make this put this exponent up on top and make it a negative. I could say 3x plus 5 to the negative 1/2 power, and then I can use a power rule. So that's another way we could have done this. So we'll do both, and we'll see what the equivalency is. But neither way is wrong. It's just whichever you see, whichever comes to your mind, and is easier for you to do. That's the way you should do it. There's no, right? I mean, the wrong way is you'd spend a million years, but whatever way makes sense to you, that you see is easy for you, do it that way. So we're going to do both just to try it out. Let's do the quotient rule. Quotient rule says low d high. Low d high minus high d low over low squared. So low is this square root thing, and the derivative of the upper part. So we want low d high. So low is same thing, root 3x plus 5 times the derivative of the upper part. Well, what is the derivative of 0, everybody? Sorry, I just gave it away. What's the derivative of 1? Derivative of 1 is 0. Giving away my answers. Yeah, so low d high, the derivative of 1 is a 0. So this first part of the quotient rule is going to cancel. And it's nice when that happens. We like when that happens. Low d high minus high, which is a 1, times the derivative of the low. Right? Low d high minus high d low. And when we do the derivative of this bottom, that's where we have to use our chain rule. So we have a derivative of the outside times the derivative of the inside. Right? We have a derivative of the outside, which is the square root part, times the derivative of the inside, which is this polynomial here, 3x plus 5. So derivative of the outside times derivative of the inside. So if we do that, derivative of the outside, well, the derivative of a square root is always 1 over 2 root the thing. Derivative of the outside, that's your derivative of a square root. Times the derivative of the inside. The derivative of the polynomial part, this 3x plus 5. The derivative of 3x plus 5, well, let's see, the 5 goes away. Derivative of 3x is just 3. That's the derivative of the inside. Derivative of the inside. So derivative of the outside, the square root part, times derivative of the inside. So low d high, that part goes away, minus high d low, over low squared. Well, the square root of 3x plus 5 squared, I'm just going to cancel the squared. The squared is just going to become 3x plus 5. Right? I mean, if you want to see that, it's a square root, and then you square it, and this squared and squared are going to go away. So low d high minus high d low over low squared. Let's simplify this. 3 times 2, that's going to put that on the top. 3 times 1, rather. This part's 0. So I'm going to have a negative, and these two multiply, 3 and a 1. And with the top of the fraction, right, because this is all, 1 is like 1 over 1, 3 over 1. This is all fractions, right? So this becomes negative 3 over 2 square root 3x plus 5 over 3x plus 5. And this is fine for your answer if you're looking for if you're doing a free response. Even the first part, even the very first answer we gave was completely fine. No need to simplify. Low d high minus high d low over low squared. Totally fine. We could do a little bit more simplifying here. I mean, there's like, make this into a negative 3/2 power kind of ugliness going on. I don't know. It's a messy problem, right? It's a messy problem. But what we have here is fine. Let's see if doing it the power rule, using the power rule, is any cleaner. So that was our quotient rule. We could definitely solve that with the quotient rule, no problem. But because we have remember, the reason why we can do the power rule is because we took the exponent on the bottom, flipped it up on top, and made it negative. And so that gives us a simpler version of the same equation. Right? Doing some algebraic manipulation, simple version of the same equation. So power rule says bring the negative 1/2 in front, negative 1/2 times 3x plus 5, keep the inside the same, and minus this exponent by 1. Negative 1/2 minus 1 is negative 3/2. So that's the derivative of the outside times derivative of the inside. The 3x plus 5 is going to be 3. Derivative of the outside times derivative of the inside. So simplifying this a little bit, let's see. 3 is 3 over 1. So negative 1 and 3 make negative 3 on the top. This negative exponent means it goes on the bottom. 2 is on the bottom, and 3x plus 5 to the 3/2 power is on the bottom. And these two are the same thing. If you want to see it, imagine this is over 1. And I take this and I flip-a-do multiply. So I would do negative 3 over 2 3x plus 5 to the 1/2 times 3x plus 5. And 3x plus 5 to the 1/2 times 3x plus 5 to the first power. These two combine to make 3x plus 5 to the 3/2 power. How does that work? Well, 1 whole is the same as 2 over 2. And when I multiply these two together, I add their exponents. 1 over 2 plus 2 over 2 is 3 over 2. Right? Just like x squared times x cubed makes x to the 5th power. Same idea. These two things that are the same, multiply their exponents, add, we get this exponent down there. So a little bit more complex maybe with the quotient rule, a little simpler maybe with the power rule. And we want to make it as simple as possible. So when you look at problems, your job is going to be to break down and identify how do you do it, what method can I use, which is going to be the easier way, what tricks can I do, and man, the AP test loves these kind of tricks. Look at this problem, and you think, wow, that looks kind of complicated. If I try to do a quotient rule with it, it's going to be a lot of messy pieces. What if I make it a power rule, right? I can change this to a simpler rule. And that you always want to be able to find ways to do that. Can I make it easier? Can I make it easier on myself? So that was that question. Questions about this? So this trick about the radical becoming an exponent, right? Use that trick a lot. Use that trick a lot. Make things into the power rule as much as you can. Power rule is a lot easier than anything else. So let's try 25. 25 says y is x root x minus, 1 minus x squared. So there's 25. Again, looking at this, what rule comes to mind? What rule comes to mind when you see this problem that you're going to have to use? What's the likely rule you're going to have to use with this one? I mean, chain rule, yes, but I mean, other than the chain rule. What situation might you find here with 25? What rule might you need? Yeah. Price for Jessica, good. The product rule, right? It's a multiplication. We will use the power rule, Jennifer, also, because this is a we could also make this, right? If we did like we did before, if I make this x times 1 minus x squared to the 1/2 power, we could also look at this, and we're going to use the power rule, right? But the product rule, these two multiply. These two are multiplying together. So I have like an f and a g, and I'm going to need to use the product rule to get this thing together. Here's a question for you. Am I allowed to distribute? Can I do this? Well, it would make my life easier if I could just put that x inside. Can I do that? Is that allowed? Is that something I could do? Would that make my life easier? PEMDAS, yes, Paraiso. PEMDAS is important to think about. Adrian says yes. Jessica says no. Let's think about PEMDAS, right? Parentheses, exponents. So I need to do the exponent first before I'm allowed to multiply. If I do this 1/2 power, it's like if I can do this, am I allowed to do this? Can I distribute inside of a square root? Not really. If I can do this with the parentheses, right, the 1/2 power, right, it's the same as doing this. And this is not really allowed, putting something in a square root, right? Not really allowed. So I'm not allowed to do that. Now, I mean, I can explain technically there's a way you can, but it's sort of more convoluted than you need. So really we're going to say no, we're not allowed to do that. If we can distribute in this parenthesis with the 1/2, I can distribute inside the radical, and I'm not allowed to do that. So let me undo all these red markings. If we can't do that, we got to use the power rule, the product rule. So let's do our product rule. We got to keep this x outside, got to deal with it. So product rule says I got, if it's f times g, and I want to do the derivative of both, it's the first times the derivative of the second plus the second times the derivative of the first. First times derivative of the second plus second times derivative of the first. And I have my f here and g here, or or here. Again, these two are equivalent with the fraction or exponent or not. So, doing my product rule, first times derivative of the second. So x is going to stay the same, times my derivative of this one is going to involve the chain rule. We could see the square root. We could do the square root. Let's just use our square root rule. Derivative of the outside is 1 over 2 radical 1 minus x squared. That's using my rule of radicals, or the 1/2 power, right? Dropping in front, negative 1/2 makes it go on the bottom. So derivative of the outside times the derivative of this inside 1 minus x squared. Derivative of the outside, the radical part was this, 1 over 2 radical blah, right? Times the derivative of the inside, this derivative, uses the power rule. The 1 goes away, the negative stays, the 2 comes down, so it becomes negative 2x, right? Derivative of the inside. So first times derivative of the second, x times this whole piece here, plus the second. So now I leave my radical the same. We'll write it as a square root, that's fine, 1 minus x squared, times the second times derivative of the first. Second leave alone, second leave alone, times derivative of the x part. Derivative of x is 1. So if I simplify this, right, first times derivative of the second plus second times derivative of the first, the x and the negative 2x are going to multiply. I'm going to get negative 2x squared over 2 radical 1 minus x squared. Just combining this stuff together. This negative 2x is the derivative of the inside this part here. So this was the derivative of the outside, right? The derivative of the outside part, the radical part. When I do the derivative of the square root, I get this. And then times the derivative of the inside part. This is my chain rule. Derivative of this inside part is negative 2x, right? Because the x squared, negative x squared I should say, brings the 2 in front, makes it x. And then these, when I'm simplifying, multiply the x times x, get negative 2x squared over this, plus radical 1 minus x squared. We could go a little bit further maybe. We can go a little bit further. I could cancel these 2's. And I could make this a common denominator with the radical. I could make this a common denominator. I could give it the denominator of a radical. Anyone know how to do that? Well, if I imagine this is over 1, right? Whole thing over 1. Over 1. If I were to, let's say, pretend I'm get a common denominator. I want to multiply by, I want to give this the denominator of it, 1 minus x squared, radical 1 minus x squared, right? Multiply the top and the bottom, give this piece a common denominator with this piece. And since the 2 went away, it just has this radical part. So I give it the radical part, multiply the top and the bottom by the radical part. Since it's the same as this upper one, these two radicals disappear. So this is going to be negative x, whoopsies. This is going to be negative x squared over radical 1 minus x squared plus 1 minus x squared over radical 1 minus x squared. See, these two, when they multiply, the square roots go away, right? Because it's the same thing multiplied each other. And now I can combine these, right? Negative x squared plus negative x squared is negative 2x squared plus 1 over radical 1 minus x squared. And that's maybe the answer they had in the book. a little bit of complicated algebraic manipulation. Recognizing that this square root is the same as this, I can get these. This is like a, if you can do this, teaching you feels great. And making you geniuses is what my life's about. But if you get to, again, if you get to here, this is fine. I mean, I would prefer maybe this, a little simplifying. But you don't need to do the square root part. I'm not worried. Like if you get to here, that's fine. But the very first part, if you get here, we're good. Maybe a little simplifying is warranted, like the easiest simplifying you can do. But the most simplified you can get, of course, the better. But this first part's fine, maybe even the second part. I don't expect you to get down to here every time. I mean, try. Look at the problem, see what you can manipulate. Because I guarantee you, your ability to simplify like this is going to reap huge benefits on the AP test. They love to do little tricky manipulative things like this. So we will continue to practice this over the course of this semester. But look at these problems, see if you can figure out how to do any other simplifying or reducing or things like that. Okay? So that was 25. What is it next? 29. 29. Other questions about that one? Let me know if you want me to go back up. X plus 5 over x squared plus 2 squared. All right. So, looking at this one, what rule, other than the chain rule, do you think we will need to apply to this? Clearly, what rule are we going to need? Quotient rule. Thank you, Jessica. Exactly. Quotient rule. We have a division here. Obviously, we're going to need to use the quotient rule. This is two functions on top of each other dividing. There's no way we can simplify this really. I mean, if we think about it, right? We always want to look and see, can we do some simplifying? Can we do some reduction stuff here? And there's no square root, so there's no like 1/2 power we can make, right? There's no, I can't cancel anything because there's like an x plus 5 on the top, and that's a whole term, right? This x plus 5. You got to think of this as like a one piece. When pieces are added together, it's like these go together, and I can't just simplify my x's, right? And these two are together as a equation. This is like an equation here, an expression. I can't separate out the x's from the two; they're combined. It's an x plus 2. So I can't simplify, I can't cancel anything, so we just have to deal with our quotient rule as best we can. So let's try to do the quotient rule here. Well, first of all, the first rule we have to do is the chain rule. I have this outside squared. So I have a derivative of my outside, which is a power rule. And then my derivative of the inside is going to be the quotient rule. So we're going to do derivative of the outside first times derivative of the inside next. So derivative of the outside power rule is just 2 times this whole thing, leaving the inside part alone, to the power of 1. Or leave it alone. My derivative of the outside was my power rule. I took the 2, brought it in front, and reduced it by 1. So I just left everything else on the inside alone. So that's my derivative of the outside. Times the derivative of the inside part. Now I'm going to do the derivative of the inside. That's my quotient rule. So low d high minus high d low over low squared. I'm just going to write the low squared part, because I know that's rule. This is my quotient rule part. So low d high. Low x squared plus 2 times the derivative of x plus 5. What's the derivative of x plus 5, everybody? Is it 5? Is it x? What's the derivative of x plus 5? Very good, a 1. But the x here is what you do the derivative of. There's no number in front, there's no exponent. Derivative of x is just a 1. X kind of goes away. We drop an x, leaves us with a 1. So low d high minus high d low. What's the derivative of this lower one? X squared plus 2. Well, I got my x squared, right? We always do derivatives of x parts. So that's going to be 2x. Very good. Low d high minus high d low over low squared. And there we go. There's my answer. We want to simplify a little bit. So what can we do? Let's see. This minus this. I can distribute maybe this 2x inside here. So this is going to be x squared plus 2 minus 2x squared plus 10x. And then if I distribute that negative, it becomes negative 2x squared minus 10x. And then I can do this x squared and this minus 2x, so it becomes maybe 2 times x plus 5 over x squared plus 2 times negative x squared minus 10x plus 2 over x squared plus 2 squared. There you go. A little simplifying. This upper part here, I just did a little bit of manipulation. Multiply these by 1, right? That's just the same, x squared plus 2. Minus these two multiplied, I did my distribution, got 2x squared plus 10x. And then I had to distribute the negative to both of these. So it became negative, right? Because this negative is applying to everything. Oops. That negative applies to everything. And like you can imagine, there's like a little box around that. That negative applies to all of those. So negative 2x squared minus 10x, distribute that negative. And then I combine like terms, x squared minus 2x squared became negative x squared, because it's negative 2 plus 1, that cancels out. And then minus 10x plus 2. All these pieces simplify to this. Anyone think we can simplify further? We have these two fractions. You think we can multiply these two fractions together? Is that allowed? Do you think I can multiply this fraction times this fraction? What would that be? So I have a 2 on the top. What would happen if I multiply the bottom parts and the top parts together, this fraction? I mean, it's just a fraction. It's just like multiplying fractions, right? Fraction to multiply, you multiply the top parts of the fraction and you multiply the bottom parts of the fraction. So top parts, I would have this x plus 5 times this negative x squared minus 10x plus 2. And, well, now I could do some distribution here, right? I could do foiling or distribute all the things and simplify this upper part together. I could. I mean, we're not gonna, but we could. We see the possibility. That's those two upper parts. The lower parts, well, here's an interesting feature. Look at this. This bottom part and this bottom part, these bottom parts here are the same pieces. So if I multiply this times this, one of these is squared. This one's to the power of 1. So if I multiply those, I'm going to get x squared plus 2 cubed. So yeah, we can multiply these fractions together, especially if denominators are like the same pieces, right? Combine those together to make this thing cubed. Because 1 here and 2 here. All of this algebraic manipulation is possible with these situations. Okay? And again, we could distribute this upper part and then get a whole another answer. I'm not going to, I'm not going to make you do any of this, but it's important to know the possibilities. If you stopped at this first section, maybe this second, you're fine. It's important to know how or what's possible to do with these algebraic manipulations. Simplifying this is, being able to simplify these are important. What was that? 29? What was next? 53. We'll go 53 over here. Is there any questions about that part? I'm going to show you any more of that. Good, everybody? Got it? All right. Again, I'm recording this, so I'll post this up for posterity. 53. Let's try this one. Oh, wait. Not 53. First, let's go in order. We wanted 43. 43. So 43 says cotangent over sine. Okay. This is 43. F of x is the cotangent of x over sine of x. It's 43. Oh, is 43 not the every other? 1, 2, 3, 4. Oh, maybe. 9, 13, 17, 21, 25, 29, 33, 37, 41, 45, 49, 53. Yeah, I guess 43 was not on the list. 43 and 47 weren't part of it. Oh. Well, okay. 41 and 45 were, though, huh? Well, I like 43. 41, 45 instead? Sure. We can do 41. I do just quickly, I like 43. I'll just do a little bit of a bonus here for you. We could do the quotient rule here. That'd be fine, right? Quotient rule. I just want to show. I want to take this opportunity to show you about trigonometry and how you can simplify it. We could do the quotient rule, right? Low d high minus high d low over low squared and be done. That'd be fine. However, another thing you can do with what do you call it? Trigonometric equations. Cotangent, right? There's certain manipulations you can do with trig, right? We know that, for example, the tangent of x is the sine over the cosine. This is one of our, right? If we recall about the definition of tangent, it was sine over cosine. Well, tangent to sine over cosine, cotangent of x is the cosine over the sine. Cotangent is the reciprocal of tangent. So we could do a little manipulation here. I could say, instead of cotangent, I would say cosine x over sine x over sine. And then I can say, okay, this is sine over 1, flip and do and multiply, becomes cosine x over sine squared of x. And so there's like little manipulations, trigonometric manipulations you can do. We did a little bit of this in pre-calc, right? When we adjusted, we simplified our trigonometric rules. So knowing those, I just want to show you, knowing those is going to be important. This is on one of those pre-calculus things to know, right? The various rules of things to know. These things here about the tangent and cotangent, along with some of the other rules, like the sine squared is 1 minus cosine squared. So I could do cosine x over 1 minus cosine squared of x. Well, anyway, there's a lot of stuff that's probably not useful, but a lot of stuff you can do here. And now we have cosine sine. That's maybe easier to do the derivatives of. But regardless, if you did quotient rule, that'd be fine too. Again, knowing how to do these rules, knowing how to follow these situations, important to be able to know how to manipulate things. All right, let's do 41. Speaking of sine and cosine, 41, we have sine 2x, cosine 2x. Okay, h of x is the sine of 2x times the cosine of 2x. Sine of 2x times the cosine of 2x. 41. So what rule am I going to use here? Obviously the chain rule, but also importantly the product rule. Sine times cosine. So h prime is going to be the first times the derivative of the second plus the second times derivative of the first. So first sine of 2x times the derivative of the second. And the derivative of this cosine 2x is going to involve the chain rule. I have my outside part, which is the cosine, and the inside part is the 2x. So the derivative of the outside, the derivative of cosine. What's the derivative of cosine, everybody? What was the derivative of cosine? Remember our rules that we talked about for trig functions. The derivative of a cosine starts with a c. All of the derivatives of things that start with c, all of the co-derivatives are negative. And so the derivative of cosine, very good, Jessica, is negative sine. Negative sine 2x, that's the derivative of the outside, times the derivative of the inside, times the inside is this 2x, and the derivative of 2x is 2. So derivative of the outside times derivative of the inside. Derivative of the cosine times derivative of the inside part of the cosine. So first time, that's our product. First times derivative of the second plus the second, so now I leave the cosine 2x alone, times the derivative of the first. And now I take the derivative of sine. So I did first times derivative of the second plus product rule plus second times derivative of the first. Derivative of sine is cosine 2x. And using my chain rule, derivative of the outside times derivative of the inside, the 2x becomes a 2. Derivative of the outside times derivative of the inside. Someone have a question? Or no? No. Okay. Let's do a little simplifying of this. I got my two sines here, right? I got my two sines here. I got my two cosines here. I can combine those together, right? Multiply those together. And this 2 in front, so this is going to become a negative 2 sine squared 2x plus 2 cosine squared of 2x. And there you go. All right, questions about that? the book may have the cosine part first minus the sine part second. Maybe it factored out the 2. You see we might factor out a 2 here. This is a negative, so maybe I put the cosine first minus the sine squared. There's a lot of, again, manipulation you can do, but this is fine. This is just great. Okay, questions about that? All right, 45. Y is 4 secant squared of x. Oops. Secant squared of x. So a lot of this trigonometry stuff. 4 secant squared of x. So we need to do a derivative of this. What kind of rule? I mean, I'm going to use the chain rule, or do I need to use the chain rule for this? Like what's how do we see this? Is there an outside part? Is there an inside part? I mean, this is just x here, so there's no inside part for the secant. But there's this squared. What does that mean? And there's a 4 here. How do we interpret this? What is this squared like secant squared? Is that something we need to think about? Well, remember when we have a secant squared like this, it's the same thing as saying 4 times, yes, thank you, exactly, Perry. So secant of x, the whole thing being squared. It's the same as this. These are the same thing. So we have a chain rule. Our outside is this power rule, and the inside is this secant. So when you see something squared, it's like this, where the squared is on the outside. You have to do a chain rule to it. There's a chain rule for this. So if we do the derivative, dy dx, power rule, derivative of the outside first. The 2 comes down in front, multiplies by the 4, makes this 8 times secant of x to the first power, right? Derivative of the outside, leaving the secant alone, right? We don't touch the secant yet. Derivative of the outside times derivative of the outside times the derivative of the inside. The inside is the secant. So now we got to look at our chart and remember, what is the derivative of the secant? Secant connected with another trig function. Secant and something were combined. Secant and something were like paired up. There was this pairing of trig functions. What did secant pair with? Look at your notes, look at your memory. What does secant pair with? Secant goes with which other trig function in derivatives? Who wants to tell me? Secant goes with which one? Look at that list of derivatives. Secant and tangent. That's exactly right. Secant and tangent go together. So the derivative of secant, derivative of secant was secant x, tangent x. The derivative of secant was secant tangent. The derivative of tangent was secant squared. d dx of secant is secant tangent, and the derivative of tangent was secant squared. So connect those two in your mind. Secant, tangent go together. Cosecant and cotangent go together. Those are connected in your mind. Cosecant, cotangent. Secant, tangent, cosecant, cotangent. And then, of course, sine and cosine are their derivatives. And so that's our derivative, right? We did the derivative of the outside, multiplied the 2, brought it in front. times the derivative of the inside. Now I could do a little simplifying again here. My two secants multiply together. 8 times secant squared of x tangent of x. I could do that. Okay, sure, or that part. So yeah, we could change the secant if you really want. You could change the secant into 1 over cosine, and the tangent into sine over cosine. I guess you could have 8 sine x over cosine cubed of x if you really wanted to. I mean, that's also equivalent. But, you know, up to you. But this is probably fine. Okay? So again, leaving secant tangent is, we don't need to change everything to sine cosine. Leaving secant and tangent is just great. So we have the two secants multiplied, right? Secant squared, tangent, all that stuff. Wonderful. Last one, and almost out of time. 53. Number 53. Y is the sine of the square root of cotangent of 3 pi x. Whew! What are they doing to us? No, cosine, cotangent. So, sine of the square root of the cotangent of 3 pi x. How many chain rules can we fit in a problem? That's the question. How many chain rules can we fit into one problem? So we're going to do a bunch of chain rules here. We got an outside of the sine, then we got an outside of a square root, then we got an outside of the cotangent, then we got this inside, very, very inside this 3 pi x. So we're going to just do chain, 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 chain all the way down until we get to the very inside of the problem here. So derivative of the very first outside is sine. So what's the derivative of sine? Well, that's just cosine. And every time you do a derivative of an outside, the inside part does not change at all. So this stays cotangent 3 pi x. So that's derivative of the outside times derivative of the inside. Our first inside is this square root. So this inside has the outside of the square root part. So we're going to do the derivative of this square root. We go layer by layer. The square root is all we're focusing on right now. Just the derivative of the square root. And we know that that's 1 over 2 square root. And I leave all the inside parts alone. Cotangent 3 pi x. So that's my outside, again, my derivative of the square root part. So derivative of the outside times derivative of the square root part. And now I did the derivative of the outside square root. Now I do times the derivative of the inside of that. And the inside of that is cotangent. Cotangent. So the derivative of cotangent, a couple things to remember. It's got a c. That means my derivative is going to be negative. Derivative of cotangent is negative something. And I remember which ones are paired up. Cotangent is paired up with cosecant. So the derivative of cotangent is negative cosecant squared of 3 pi x. So that's my derivative of the inside part, that cotangent part. But this cotangent also has an inside. Now I go in the next layer down. I do the derivative of this inside, my 3 pi x. So I got layer by layer. Derivative of the outside, the sine. Then I did the derivative of this part, which has the outside of the radical. Did the radical derivative. And then I do the cotangent derivative. Did this cotangent derivative. Now I do the 3 pi x derivative. And what's the derivative of 3 pi x, everybody? In the chat. Derivative of 3 pi x. Anybody know what that is? Derivative of 3 pi x. Is it 3? Is it pi? 3 pi. Very good. Because the x drops away, and the 3 pi is a number, right? That's a constant, so that stays just right there. And I'm not going to bother simplifying this. This is enough for me. We could put these 3 pi in the top of the fraction here, and then maybe the cotangent would cancel, and, well, no, because that's a cosine inside. It's like this, more like. Anyway, complicated, not necessary. What you have there is fine. No, I liked it with the e, Jennifer. Better with the e. 3 pi's? Yes, please. Where can I get me some of that? All right. So good job, everybody. Lots of practice. Well done. Here's what I want you to do. We're out of time now, so here's what I want you to do this evening. I have put a handout. I'm going to put up a handout. Actually, let me show you this handout on our Schoology page. Let me go to our Schoology page. So the handout, applying the chain rule. This is a handout you can fill Kami. Handout here. Oops, fine. Okay, view it. Show it to me. This is the handout here. And what I would like you to do is fill this out. Fill out the answers here on Kami. Let me show you. So, I haven't really got to this. So there's composition, chain rule situation here. And questions about, zoom out. For example, like, what is g of f of 1? So using the chain rule to try to figure out what all these are. So g of f of 3, for example. G of 3, you look up g of 3, here's g of 3 is 6. G of 3 is 6. Let's say 1. G of 3 should be 6. I don't know what this is. And f of, well, anyway, I guess it's supposed to be 1. F of 1 is 3. So you're looking up different things. G prime of G5 of G of 5. So G of 5 is 4. Here's 4. And then G prime of 4 is 1. So you're looking up the answers like that. Do that for these. Try those out. A little bit of chain rule practice. And then here, write down the outer function, inner function, derivatives, and how they all work, and apply the chain rule to these problems here. Questions there. Type those answers up. And then here, just check yes or no and find the derivative. Is the chain rule needed or no chain rule? And find these derivatives of these 4 questions here. So some practice for you. Now that we've seen it before, try these questions out. We'll go over this next time. Until then, I will see you all later. In the chat, type goodbye. Once you type goodbye, you're free to go. Thank you, everybody.